Sweet. Okay. I'll give people a few minutes. Maybe 1 minute. I don't know. Oh, I didn't ping, did I? Sweet. Anyway, so today we're going to be doing Bitboards. I won't jump quite in right yet because I'm hoping maybe we'll have another person or two. But I think what we're going to do is probably just make Bitboards for common use cases. I'll probably just do Connect 4 because Connect 4 lives rent-free in my head. So that'll be what we start with. Maybe we'll do some other games. We might do chess. We might do, I don't know. We'll probably talk about chess because actually implementing it entirely would be a little bit challenging. But yeah, maybe we can just get started. So I just went ahead and made a very basic file. Do you guys know what a bitboard is? Let me start with that. Like, do you even know the definition, like, or what it's intended for?
No, but looking at this, I already have an idea of what it might be.
Okay. Anybody else? I'm assuming Cyberpunk knows.
I imagine you efficiently represent board states with a bunch of bits.
That's a great starting point. So
yeah, that's what I was going to guess.
Yep. So all I made here is just a function that just prints out a bitboard, and so I have it like currently it's just printing out a binary number effectively. So this is, you know, I'm telling it 1. I just instantiated the binary number 1, and this is just printing out like the number 1 in binary in a 64-bit like container, and then we just left shift it 1. So I'll also ask, are you guys familiar with bit shift or bitwise operators in general?
Yep.
Yes.
Okay, that's good. So yeah, obviously we're just shifting the 1 over 1. However, you know, a lot of the time, if you're playing a board game or doing something that involves like a 2D surface that has things that move on it, more generally, you want to think of just like you can think of that board as a like a 2-dimensional surface. You can think of the binary number rather as a 2-dimensional surface where you're just like packing bits 1 by 1. So this is just the leftmost bit in my binary number here, and my second leftmost bit, third leftmost bit, and so on. So the 1 is now down here, and then moving left would correspond to like shifting that 1 over a spot, right? And we can like we can also go ahead and like shift this over by 8, for example, which is, you know, it's an 8 by 8 grid, so that's equivalent to moving it up 1, right? We've now got the 1, we've got the 1 moved left, and then we have the 1 moved up. So, you know, using this, we can sort of do graphical quote unquote like operations on this board. So I guess going with the example of Connect 4, how would you maybe start to represent the game? I guess I'll say that we're going to want 2 functions, maybe one to place pieces and one to check if we've won. So how
I would assume you need 2 of these, 1 for each player, because how do you distinguish an empty space from red from yellow?
Yeah, exactly. So we're going to want to keep track of a pair of bitboards as the board of the game. So we're going to want to have like here, I'll just go ahead and put it in the main function, I guess. We'll make a bitboard called red board, or we'll just say red equals 0 to start. 0 0x. I think like that. And then same thing for yellow. So we'll just have both players start as 0. How would you make a move on a board? So let's say like I want to make a function called like int, void make move, and it's going to modify. What I'm going to do here is make it modify the 2 boards. So we're gonna pass by reference like a red and a yellow, like, what would I call it? Like we pass in the two bitboards, and then we're gonna pass in like an int column. And oh yeah, we also do need the is red. Thank you, AI. How would you go about? Yeah, I gotta keep track of who's making the move. So, how do you start to implement this? We're gonna like go ahead and say like, you know, we're gonna call this like make move. Yeah, red, yellow, 3, true. We'll just do 0 indexing for simplicity here. Yeah, how would you? Yep.
My first guess would be we can, if we OR the bitboards together, we should be able to use some like leading zeros trick maybe to figure out how many like free cells there are basically if we were dropping a piece.
How many free cells? What do you mean by free cells?
The two boards to define empty spaces.
You can do that. We can start with that. But what are you gonna? Sure. What's next? I'll just say like uint 64 full, or like yeah, I'll call it full. Full board. Yeah. Now what?
If the
Ignore that.
It's because it's columns that makes it hard. If it was rows, it would be.
Why do you say that? Like we're telling you. Mm-hmm.
Could we get a visualization of like how
rows.
each bit in 64 like from LSB to MSB like corresponds to a row and column? Like I think we're.
The way I made this right now is this thing.
I would bit shift it rightward. Like if it was inserting per row instead of per column, I would bit shift it rightward by 8 times the amount of columns to shift the column that you're focusing on to the bottom, and then you can just ignore everything on top. And within that column, you can shift it rightward step by step until you find an open space, and then place it there, and then undo the recorded shifts to place it in the original.
Okay, that is great and a working idea, and we'll start there. But you can do a lot better. You can do much faster, like bitwise tricks to hack around.
That's just my first
idea. Let's start with that. I think just to make this simpler is like we're gonna go with let's do like a I'm gonna say void insert coordinate, because I think we were starting to get tripped on like coordinate systems, so I'm just gonna go ahead and start with that. My coordinates like so I think, you know, I did this like left to right because I was printing the binary numbers left to right, and then I just added like new lines between each row here. But I think we're gonna want x being 0 to be the leftmost thing. Yeah, that seems reasonable, right? Like if the number 1 corresponds to a 1 being in the bottom left. So let's go ahead and design it like that. And by design it like that, I really just mean change my print function to put the x's in reverse order. So we're gonna say x equals 0. Yeah, exactly like that. Oops, what happened? Oh yeah, we're not calling it anymore. Print bitboard. We're gonna print bitboard, and we're gonna say we're just gonna say 1 ull. So this is just saying 1 with line breaks. Okay, I screwed something up. This x and y are swapped. Was that swapped before? It must have been, right? Wait a minute, what? What did I do wrong? Somebody correct me here. What did I screw up? Y times 8. No, that should be x times 8. That's right. Oh, we're iterating on x as the outward. Wait, that's not right. These two for loops are swapped. That's the problem. There we go.
Do a shift just to check if you.
Sure. Yeah. That's a good point. Yeah, let's go like left shift by 1. So this should now move the. I did swap the x and y.
Yep.
Yes, y times 8. Yes. Yep.
It's in y times 8 plus x. Yep.
Yep. Yeah. Exactly. Okay. Sweet. So that's working now. So just that makes it easy to like, this is 0 index on the x column, so we're just doing normal coordinate like notation now. Okay, so we're gonna insert a coordinate in the x and y, and oops, it already implemented it for us. Someone tell me how to do this. Don't peek at the AI answer.
I wasn't even able to read it before.
By the way, is this big enough? Let me make it a little larger.
There we go. Now I can read it.
I would assume you have a single 1 at the 0, 0 position. And since y is by row, you would want to shift by 8. And x is by column, you want to shift by 1 per.
Tell me what the line should say. So, I think that all sounds descriptively correct, but... yeah, it's totally hard. Sure. That's what you said. I'll give it to you.
That is basically what I said, yeah.
So what we're doing here is
you just work together, right?
Yeah. We're taking...
It'll leave it set.
It'll place...
Yeah. We're taking a 1. We are left shifting it, which is the same as like moving the... Like, we're changing the x index by x because we're not multiplying by 8. If you were to pass in 9 here, it would go up a row, or 8 rather as x. Even if you passed in 8, it would go up a row and like stay in the same position here. But like we're assuming
our next board is 8 by 8.
Yeah, this is okay. Well,
yeah.
We will contradict that feasibility later.
Okay.
For now, we are
make that much of a difference. But it will eventually for implementation details.
Yes, yes, that's correct. Which we'll see soon. But anyway, for now, so does this make sense to everybody? Does anybody not get what's going on here? We're shifting right, we're left shifting 1 to move in the x direction. We're left shifting 8 to move in the upwards direction. So just left shift by y times 8 plus x to go to move the distance that you want to move in this coordinate system. That's the idea.
Yeah, it makes sense. I don't know when we're going to want to use insert coordinate, but I understand what the code is doing.
Well, when we're making a move, we're going to want to... should I explain Connect 4? Anybody not clear on what we're building here? Like what we want to do is we're gonna say drop a piece in column 3 here, and then it's gonna fall down. That's what happens when we run make move. Or the 1's gonna be placed on the bottommost open slot on that column. So I'm imagining we're gonna call insert coordinate in make move.
Okay.
Yeah.
So that's the idea here. So. We're going to say insert coordinate. Yeah, so we don't know the x value yet, so I'm just going to leave this as question mark. This is inserting on the full board.
You mean the y coordinate, because the x coordinate is column.
Yes. Correct.
Yeah.
How do we figure out what the y coordinate is?
Since the column is the positions are sorted and whether or not there's a piece in them, you can use binary search on it.
You can. We're gonna ditch the for loop entirely in a moment, so I'm going to not go and implement binary search. But we can start with. We can start with a simple for loop and just walk up the column and just check,
Yeah,
so
that's what I was thinking. Right shift repeatedly until there's a 0 found in the position.
Yeah, wait. Let's
right shift by 8 repeatedly.
So
yeah,
if we have if the bottom of the column has a bunch of 1s, then if you add 1 to it, the first 1 that you have will be in the right spot. Is that
you're saying we take the column as a binary number, then we add 1 to that binary number, and since all of the lower bits are...
bit is like the
Yeah.
location we want.
That is a good idea, although...
a bit hard to do.
That's a cool idea, however... Yeah, there's no easy way that I can think of off the top of my head to, like, populate this column into a binary number. One trick that you could do...
If the X and Y coordinates were switched, it would be easy.
Yeah. Well, yes, it would be... Yeah, it would be...
Them.
I think...
Start.
So like, if you have your coordinates be like if we're playing Connect 4 with gravity moving like rightwards, then like each row is a binary number, and you can just take a bit mask and steal out that row. That would totally work. We could do that. We're going to ditch this. Let's just start with the for loop, and then we'll do other cool stuff. And that is a workable idea, to be clear. But I think it's probably not where I'm going to go with this.
Maybe a while loop.
Sure. While loop, whatever. For loop, anything will do. We're going to say int row equals 0, and then this will be the row that we end up populating in here. Then yeah, sure. While row is less than 8. We're gonna actually say row is, while row is less than 8. I think that's fine. So we're making this mask that corresponds to just a bitboard for the single spot that we're checking. And if there is a thing there, this is just saying if the full board and mask, so if in the intersection of the two bitboards, the spot that we're checking at and the board itself is 0, if there's nothing there, then we break out and we've identified the row that we want. So that's how we know what row we're trying to look at. And let's go ahead and do... also I did this wrong. This shouldn't be full board that we modify. We should be modifying...
modifying the...
is red.
Yeah.
Yep. Okay, so now we're going to go ahead and...
AI are using it. It looks really...
It's just the ChatGPT one. I don't know.
Okay.
Yeah, or sorry, not ChatGPT one. The what's it called? GitHub Copilot in Vim.
Copilot. Yeah. I'm using a different one, and it kind of doesn't really do what I want. Because the stuff I'm coding is just insane.
Invalid moves.
What'd you say? I missed you.
Oh, sorry. I was saying, are we worried now about invalid moves?
We'll start getting worried about invalid moves. But for now, let's just first of all, I just want to check that this is even right in the first place. So let's just drop 3 things on. Okay, sweet. So we've dropped 3 things, and looks like it works. Let's try some let's go ahead and we're gonna print both things, and we'll put this in a little for loop. We'll make 4 moves, and for each move we'll just do the next 3 lines like that. Okay, and that's hard to read. Hold on. Yeah, that'll be better. Okay, so we have...
I'll just put a color the text.
What's that? Oh, we could. We could color it.
Color them red and yellow for the boards respectively.
Right now, I think the behavior might be that if you try to drop more than 8 pieces into a column, it might overflow into the next one.
Yes, it will. I think, actually, well, we're checking rows less than 8. So yeah, row's gonna plus here, and then we end up adding like row of 8 here. So y is gonna be 8, and you're gonna overflow into the next column. So we can go ahead and we can add checks for that. Although that's kind of boring. Like I think everyone in the chat knows how we could. Did I just say chat? What am I, a streamer? I think everybody here knows how you would implement that. So I'm just going to ignore that for now, because we're going to go and change this implementation right away anyway. I'm going to suggest that there's a way that you can do this with like a bit shift or 2.
Yeah,
Like,
that's what I was wondering.
We do not need any loops. And like once you start introducing loops, like you should be questioning your life, because like that is not the philosophy of Bitboards. That's not what we're trying to do. Because like the whole point of this is we can like write pretty much everything that we need here, and like, you know, in the range of like 10 to 20 bit shift operations, which is 10 to 20 CPU cycles, which is like a couple nanoseconds. So
bit shifts are really fast, and so
Yeah.
are all the logical operations. Remember that one Matt Parker video? Somebody sped up his code by like, what was it, 41
Yeah.
billion%?
Yeah.
A bitboard representation of the letters.
I don't know the video, but yeah, it sounds plausible. That's what it does. Okay,
Yeah,
so how would
his original code took 4 months to run.
yeah.
The one that they ended up making using bit shifts and bit masks ended up taking like what, nanoseconds? I don't remember what it was, but it was
Yeah, Bitboards
near
are
instant.
nice. Well, I'm sure the program didn't run in nanoseconds. Like a check could run in nanos. Like a bit.
Yeah.
We're gonna hit nanoseconds. Like we're gonna hit like
Few
single-digit
milliseconds.
nanoseconds for board validation or board win checking in Connect 4. That's the goal here. But
Let me go
beside
find
the point.
video.
Okay, how are we gonna do this? How are we going to figure out what is the spot that we want to go only with bit shifts? We have this full board representation. I'm just gonna print out the full board representation here. Yeah, print bitboard. Yeah, we're just gonna print it out. We do want this true, right? True. What was this? I'm getting rid of the line breaks thing because I already said what binary numbers were. Okay.
Oh, yep, found the video. Viewers' improvements reduced my algorithm runtime from 32.5 days to 6.7 milliseconds.
Yeah. Yep. Okay. So we now have a bitboard for the full board. I'm gonna like comment out some of this stuff. How are we gonna use that? Any ideas? Anyone want to throw anything out there of how like? Oops. What did I do?
So the biggest question I'm having
Oh,
is,
I know what
how
I
do
did.
we find out how high the column is?
Yeah. I'll give you a answer, or I'll give you a hint answer. You don't. There's no need to. You can solve the problem without even doing that. Like we're not gonna. Yeah. This insert coordinate kind of works well for the for loop implementation, but we're just gonna figure out the mask without even knowing where the coordinate location is.
If you add 1 to the position at the if you exploit how carry works in the ORed bitboard, it should place a 1 automatically at the.
Sorry, say that again. I missed you there.
Oh, so if you take the ORed bitboard and then you add a 1 basically to the column that's we're dropping a piece into, basically it should just carry basically into the next bit.
That's what Deerwood was saying earlier, I think. The problem is, how do you actually extract this line and like just put it directly into a binary number? That is.
You don't need to. You can shift it. It's a single bit increment. You can shift it wherever you want to in the mask.
Oh yeah. Okay. Yes. In that case, yes. Yeah, but that's not. We're not talking about adding
to the right, not to the up.
Yeah. This is also true. Are you saying add or shift?
Yeah. You shift a single 1 into the 0, or would it be topmost or bottommost? Whichever one of those correct directions is on the column, you shift a 1 to that position, and then you add it to the bitboard. And if it doesn't overflow the 8-bit column, then it should just give you a 1 at the correct column position.
You're saying we add a number to the bitboard. What that number is, we don't know yet.
Arithmetic add. Well, I mean, we do. It's just 1 shifted right 8 times the column we want to add to.
I am not following the solution, but let's try it and see what happens. Say it again. So what am I writing here?
If we want to write to the 0th, if we want to drop a piece into the 0th column, we would just add a 1 to the board to get the index, the mask of a column we dropped into. So
What should I write? Or you're saying?
okay. Line coding is really hard. 1 second.
All good.
So we're gonna need one variable that's like mask of the piece we're dropping to. So that is gonna be one shifted left, 8 times the column we're dropping to. I think
One shift. Okay, so
that's what we need.
I mean, one left shift the column that we're
8 times the column we're going
8 times
for.
the column. So you're moving up. You're moving vertically an amount that corresponds to the column.
Yes, I believe so. And then you add that column mask to the full board, the red or yellow board. The sum of those two, assuming you don't get overflow, I think will give you the mask index of like the bit that should the position that you have shot by that new.
Is this what you're saying? Like that?
Not equals. I would use another way to read it. So I would say like dropped mask equals like full board plus all mask.
Dropped mask equals where it equals the full board plus that thing.
Yes, and so
I mean, I think I know what's gonna happen here, and I don't think it's what you think is gonna happen here. What did I do wrong? Oh, we're not doing this anymore.
we're not actually using that variable yet. Hold on.
Yeah. So we're.
So then we can
we'll say
the
or equals dropped mask.
If it's this move we or
Right. Oh yeah. Sorry. Yes.
Yeah.
Good call. Red. Yeah. Red. Yellow. If red is red. Okay. Good. Good. Yeah. That's sufficient. Oops.
So, the drop mask.
Oh.
If the rows and columns are in the right order, I think like the drop mask might have the right like relevant column, but then it'll also have all the other stuff.
So yeah,
Right.
so dropped mask here. Like what we're now doing. Let's watch what we're doing here. So we get a full board. At this point, the full board is like on iteration 0 here. The full board is empty. So it equals red or yellow. Both red and yellow are empty. The column mask that we passed in was 3, right? So we're gonna shift 1 left by 8 times 3, which is going up 3. Then dropped mask is just going to be 0 plus this thing. And then we're just like or equalsing the full board with this 1. Okay, should I give a hint?
Yeah, I'm drawing blank here.
Do you get why that doesn't do? I'm not sure where you're hoping this to go, to be honest with you, but do you see why it doesn't work? Do you get the idea?
Not exact. Hold on. What output am I looking at exactly right now? Are we dropping 3 pieces again still?
Yeah, so this is after having dropped. This is the red board after having dropped 1 red piece in column 3 from an empty board. So like in theory there should be a 1 here.
Work if the X and Y were switched.
Would this work necessarily if the X and Y were switched?
I think yeah, I might have. I think we're doing a Wait, what's the next output after that? Does it actually drop the 3 pieces correctly? Like where the
Yeah, okay, yeah, it seems like it does.
Oh, okay, yeah, I gave it transposition of it, basically.
Yes, okay, wait, so that might actually
again,
be perfect
like
then.
the original solution I was talking about.
3 plus I. Yeah, this will work. I think that'll work. Oh, cool,
So
yeah, that works.
Drop mask is full board plus column mask, and so the like in the column where you're dropping it, I think this does the correct thing. But then drop mask, wouldn't that also contain all of the pieces in all the other columns? And if so, you don't want to OR that with red and yellow.
Oh
right?
yeah. Oh shit. Okay.
So yeah, it has that.
So
Yeah, that's true. That's true.
You
That's
need
true,
to OR
yeah.
it with
Like
hex
I
FF
think
or 255 shifted left to the right column. That would give you the right mask, or and it with that, rather.
I agree. That's one way to do it.
I missed you.
If you and it with hex FF or 255 shifted left to the correct column, or
And
like shifted
what?
left
What am I ending with? What am I ending
So
with?
that whole sum, full board plus column, need to match with 255 shifted left 8 times column, just like column mask.
Okay, I think this is getting complicated, and I think there's and also we're doing things transposy. I'm going to suggest a different way.
Wait.
But are we doing left gravity here? I mean, you could go and change your coordinate system, I'm sure, but like to make it work.
Okay,
but
there's clearly there's clearly an intended solution in mind that doesn't involve like.
There is an intended solution in mind. Maybe this makes sense in your head, but I'm having trouble, and also I don't like ands or like arithmetic ands because this gets confusing in terms of like overflow things and like what happens if the I don't know. I'm finding this slightly harder to visualize than I think it needs to be. So how am I going to present this? I think we might need to start with the assumption that the board is less than 8 by 8 here. Hold on. Okay, so I'm going to flip the bits of the whole board. Let me start from scratch here. We're going to.
So inverting the board puts a 1 at all the empty spaces.
Yeah, we're just going to invert the board first. So invert. Yeah, okay, so we invert the full board. This is going to look at first like just a box of 1s when there's nothing on the board. Now what I'm going to do is left shift it by 1. Upshift it, like physically upshift that inverted full board by 1.
Is left shift by 8?
Up 1. Yeah, exactly. Invert equals invert left shift 8. Yeah, left shift 8. Now we're also gonna go up 2, which is gonna be invert left shift by what's it called? 16. Okay, so now we have like what you should be imagining in your head is like you have this like city skyline looking shape here, and we've now like figured out actually what I'm going to do is I'm going to invert both of these and then we'll talk about it. So we're going to invert the up 1 and up 2. This is going to be a Boolean inverse. Now what we've done effectively here is just shift the skyline up by like 1 coordinate in the upward direction. Does that make sense?
Yeah, I got it so far.
So now...
Wait, so like, it would be like a whole row of 1s on the bottom, and then a second...
2 rows of... Yeah, up 1 is going to be that. I'm now realizing up 2 doesn't want... Oh, I don't want up 2 to be that. But yeah, up 1 is going to be the whole board, just as though you've like shoved a piece on the bottom of each column. Or alternatively, just dropped a piece in each of the columns. Now I'm gonna make one that I'm ignore up 2. I may have been hallucinating an idea with that. What we're now gonna do is figure out the set of playable pieces as up 1, or sorry, full board. No, up 1. Sorry, what am I saying here? Playable. I'll call it playable equals up 1, and like bitwise and the inverse of playable, or sorry, the inverse of full board. So what we're doing here is we're saying that skyline shifted up by 1. Remove everything that was in the original skyline. So what I'm going to do now is I'm going to just like we don't have the infrastructure for me to actually make an example here, but
we should have like this thin line that's just like the top strips after we imagine dropping a piece in all the columns.
Exactly. Yeah. So here I'll make a quick example. Let's do I'm gonna say red starts with like we're gonna say 0B, so Boolean 01 01 01 01 ULL, and yellow will be the same thing but 10101010 ULL. And now we should be able to call this, and like what we should see here is like the second line from the bottom should be filled on playable, if I got this right. Print, we're gonna, yeah, so we print playable. What's printing? We don't, I'm gonna delete this for now. We just want to print playable. Okay, I probably got something wrong because that looks weird. Anyone know what I did wrong? What is that? Let's print everything. Print bitboard. We're gonna print the full board. So why is it starting like this?
Oh, I think you meant to write hex 020202 it's been so on instead of 10101. Maybe that. I think you might have gotten
my goal is
binary multiplication by 2 and hexadecimal.
Oh, that's hex, not binary.
Oh, oops.
Yeah,
yep,
that's
it.
what Jakob Math says in the chat.
Oh, yeah. Thank you. Yes. Okay. There we go. Sweet. So yeah, the full board is now all ones. The next row, like we've gotten just the set of playable pieces. That's why I called it playable. These are like the options that we can use here.
Oh, and this works regardless of how many ones are in either of the in full boards, right? This will always put a 1 at the top of the column.
Exactly.
Regardless of the boards. That is clever. Okay.
So now we're gonna go ahead and just like and that with a like strip corresponding to the column. So I'm gonna say like
which is just
XFF shifted right 8 times column.
Exactly. Yeah, that's already
FO.
Or actually, excuse me, hex FF ULL because length specifiers.
Hex.
No, that'll only be the row. You're trying to get.
That's the that's the column
of ones.
Yeah, we're trying to get the column.
The column of ones would be 80808080.
This is right. What it's got here is right.
No. Right. Good. I'm flipping it mentally. I'm flipping it.
Yeah, me too. I keep.
Yeah, so
I keep getting columns over and over again.
Yeah, so that should be like a whole column of ones on the left edge there.
Yeah, to be clear, like in case anyone didn't notice, this is hex. We're back into hex. This was binary here.
Okay.
Sorry for the confusing swaps.
You shift it over by the column amount and it together, and you get only a single 1, which is the exact position that you're going to be placing the piece.
Exactly. So we're gonna now say append. I don't know. There's probably a better word for that, but we're gonna say if is red. Yeah. Okay. And get rid of all that junk. Print. Let's print. Sure. Let's just go with that.
I wonder if this is actually any faster than what Cyberpunk was saying.
I don't think I don't think it is, but I think it's easier to understand. Maybe you could argue with me on that one.
It's
I don't know.
About as fast actually looking at the operation count.
I think it probably is.
I'll bet the dominating thing on the runtime is probably literally checking if it's red's turn to check or to append it to.
That could be
probably actually the chunkiest thing.
There's a method to do it without a branch as well.
Sure.
You can just multiply by 0. And then
you would just write to both. You would end up writing something to both bitboards, so I was literally just writing the same thing back to the original.
Yeah, but it would be faster.
I think what Naifakosi was saying like is you can do like red or equals like append times is red like that or like but times is slow though, right?
Yeah, times
and then
is slow.
The other one would be times not is red. Well, I mean, I'm sure a real compiler would figure out that you're
a real compiler would simplify that down to because it's a Boolean, it would simplify it down to a logical AND.
To an AND, but it would have to be an AND FFFFF, not just an AND like.
Yeah. Which I mean, you could just
with the Boolean itself.
You could do some -1 trickery.
Yeah, you can do. Yeah, that's true. That's true.
Yeah.
Or just define a constant. But anyway, I'm just gonna leave it like this for simplicity's sake. You all get the idea.
Yeah, good enough.
A lot of this ends up like if you actually want to look at the runtime analysis of these things, a lot of the time it'll come down to branch prediction. I think in this case, your branch prediction would probably be quite bad because you're literally oscillating each time you make a move. So this will probably be quite slow when you.
It might just unroll it into a red, not and red yellow turn. I don't know. Probably.
Maybe, I don't know. Anyway, does it make sense how we got to there? Any questions?
Yeah.
Before I move on. Okay, I'm gonna go ahead and do. Let's do wind checking. Actually, well, we can also make. Let's go ahead and just. I was gonna say let's add checking for if we hit the top, but like. I think it makes sense. I think we can figure out how to do that. So let's just do fun stuff. No important stuff. Let's just do fun stuff. Okay. We'll do. Let's call it bool is 1. So what'll I guess the way that I'll. Oh no! All the answers are right there. If we're gonna say if. We're gonna pass in a single bitboard, and we're just trying to check if there's a line of length 4 on that particular bitboard. So we'll say you int 64 bitboard. Don't look at that. No cheating. How are we gonna do that? How are we gonna quickly figure out if there's a line of length 4 on this board? This is just one player, to be clear. Like it could be the red bitboard, for example. Any clever ideas as to how you could detect the presence of a line of length 4?
First dumb idea is shifting a window of 4 ones leftward and ANDing it until there's.
That would work. That is a workable solution. We can do way faster. It is a
slow solution.
That's true. No for loops. No loops.
So this is not. I don't think this is easy enough to translate into like C code, but like there's a polynomial that like is one like you take all the products of all the 4s and put it together, and then you compress it. I don't know.
What are the 4s? All the 4s? Oh, I see what you mean. You're saying like if we were to write this as a polynomial, it would be divisible by the polynomial that is given by each line of length 4.
Yeah, like if we pre-ask a like.
That is a great mathematical answer to the question, but that is a much.
Memory, I think.
Yeah. Implement polynomial division just to solve connect 4 wind checking.
Well, I would call what do you call it? Like one of the normalized form for logic things, and just like paste that, and it would be like 1,000 ands, but it would be the right 1,000 ands or something like that.
I don't know what you're talking about. the logic of what?
Okay. There's something in the chat now.
Oh.
An answer?
Jack of Math sent a...
Ooh, yes! Perfect!
That is really clever.
Yes.
And
okay.
You do the same for...
Yes, that is very clever, and that is what we're going to go with.
Diagonals and... Yep.
Yes.
Yep.
However, there are problems with this that need to be fixed before we drop it into our code directly. Anyone have any ideas of what would go wrong with this if we just copy-pasted naively?
Wait, sorry, can you walk through what that code, like how that works?
Yeah, and I think here. So I'll go ahead and begin implementation here. So let's say,
you're taking the current board, and you're ANDing it with the board shifted left by 1. So any run of 4 gets like shortened down to 3, and any single 1 bits get wiped out because the bit next to it was a 0. Then you AND it with the board shifted left by 2, so that shortens it again, and shift left by 3 until you have just a single 1 bit. And all other bits have been annihilated by being ANDed out. The only 1 bit remaining existed in a run of length 4.
all on the same page. I think that was a good explanation. I won't reiterate any of that. It sounded good. The idea is we're just checking, like, you know, if you can shift them 4 times and them all together, then that means that all 4 of them were 1s. Cool. Okay, we're gonna run with that then. You need the last term. Yes, yeah, that's the problem. Is no, you got the. I think you got the right number of things. But yeah, the problem is overflow. Overflow is the big problem here, and that's where this kind of where our world comes to a crashing halt. Luckily, the and left several columns. What do you mean by that? I'm not sure what and left several columns means. But I don't know what you mean by that. Left several columns. Oh.
Like the last 3 columns, maybe?
Yeah. So I think, yeah, in order to resolve the issue of overflow, to be clear, the overflow that we're checking here, like, in the case of the left runs, which is the one that I've written so far, the overflow that we're concerned about is like checking for 3 in a row on the end of the row and then 1 on the next row. That's the immediate danger in this case. Or actually, I think it would be like these 3 and then this one, given the order that we have for the binary number. Does that make sense? Is that clear?
Yeah.
You would have to, yeah, so you could go and implement this and say, like, you know, check the left half of the board for like things that are flowing over the left half of the board, and then the right half of the board for, like, you know, things over here. I don't think that there is if there's a clever way to solve this, to work around this, I don't know what it is, and I'm not sure. To make sure you check positions you didn't shift in from another row. Oh, that works. Does that work? I think that works. But if you and the whole thing with the left several columns, yeah, that
would be
works.
ANDing it with a F8, 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 F8. I think.
Right. You would what? Not F8. F8. Yeah.
No,
F8.
Or it would be the other way around. 1F.
I'm just gonna. Yeah. Correct.
Yeah.
Right.
Yeah. F8. Yeah. Because it. Yeah. It'll. Yeah.
Hold on. Let me. Left. I'm just gonna call it left several columns. My immediate question now is going to be how are we going to implement this for diagonals? I guess you would have another. Okay, no, I can see it.
I think it's similar.
We can
for vertical. Yeah, for the columns it would be left shifting by X left shifts 1 plus 8, or no 8, 16, and then 24, right? For the columns. And for the diagonals, it's 1 plus 8, and then 2 plus 16, and 3 plus 24. Or minus. For the other diagonal.
1 plus 28. Huh? I lost you.
Okay, so for the columns, checking the columns, it's very similar, but instead of shifting by 1, 2, and 3, you shift by 8, 16, 24. And for the diagonal...
Yeah, that's correct.
I was together.
Yes, that's correct.
You shift by 8
I was asking
1,
about what is the mask that you have to apply, though?
Yeah, that...
You can do it. It'll work. It'll work. Thank you. I didn't even realize that this was an option. I've just always deferred to the fact that the Connect 4 boards that I'm ever interested in using are 7x6. In which case you can get out of the necessity to actually run this and you can save some time. But this is clean though, so I appreciate
and in fact, you could just like trim down the board from an 8x8 and only like display. Yeah.
So if you so what I'm doing in my Connect 4 implementation is just you can't insert anything into the last column, and because of that empty last column full of zeros acts as just a stopper, so you can't implicitly or explicitly shift anything like through the row or through the top of the column either. Like it doesn't really make sense to do that. But this effectively achieves the same goal, but this also extends to 8x8 boards, which is nice. Okay, so we're right shifting one. Yeah, okay, so this should be good. Up runs, how are we going to do I'll call it vert runs, vertical runs.
I already said it's by 8, 16, 24.
Yep. 16, 24. Okay, sweet. And now this should not be left several. This should be what? That's not right. That's not right.
It's saved to Discord, but I don't know if it's saved.
The chat is. I'm unfortunately not screen capping the chat. Sorry about that.
But as long as this general channel exists, the chat exists.
That's true. Okay. Oh, I think Craig does record. I think maybe you have to pay and it'll record chat. I forget. Anyway, down several. What should this be? I'm pretty sure this suggestion is incorrect. Oh, actually, maybe it's not incorrect because
the overflows.
The overflow fixes it. No, I don't even think you need a down several.
Yeah, I don't think you need to worry about the overflows for the vertical ones because they're only going by.
Because you're going to shift in zeros anyway. Yeah. Okay. Yeah. Good point.
For the diagonals, though.
Yeah, diagonals will be a little bit of a mess.
The first idea is, of course, to do the 8 plus 1, and then 16 plus 2, and 24 plus 3. And also 8 minus 1, 16 minus 2, and 24 minus 3. To get both the diagonals.
Yep. It filled in the numbers there. You guys could do the math if you want to, but yeah, okay. 9, 8, 18, 27, and I didn't even rename it. Diag 2 runs. But what are the things that we have to check it against? Are there any? I guess there still are ways that this could be split across rows. So how would you mask it? I see the answer in the chat, but that is no one's allowed to look. You guys have to tell me.
Because of the way diagonals overlap, can't you use the same mask?
Yep. Yeah, same mask will work. Okay, so we're going to add this to left several. Sweet. Actually, hold on, sanity checking.
Wait, I don't know if they'll both get the same.
Almost the same. I think you need to OR in a few more bits at the bottom to account for the corner. Right? Maybe.
hold on. Diagonal runs, so we're shifting. Bitboard, hold on, I just want to make sure I geometrically know what's going on here. Right shift 7 is equivalent to this diagonal. No, this diagonal. Because it goes like this. Yeah, so the right shift 7 is, we're going on along this line. So the case that we need to worry about here is like if we have like 1, 2, 3, 4, something like that. Right? Am I getting that right? So, no, I'm not getting that right. What is this one, right shift 7? Does that work? Someone sanity check me. I'm not confident. I think it works.
I am also not confident. Could always write a test case.
We could. I don't know what I'm even trying to test though yet. Hold on. So if we have four, like, what is the problem? If we left shift this one, if we left shift this one, like a line of 4 like this, a diagonal of 4 like this by 1, we would have like 1, 2, 3, and then 1 over here on the same row. Now, if we now collapse this using this, like this thing of right shift 7, right shift 14, right shift 21, it would push this one, it gets right shifted back onto this one, the next one gets right shifted back onto this one gets right shifted back onto this one. So the one that you end up with is in the section of the board that we've cut off. So I think that's right.
So it just works in general still.
I think it just works as is.
We'll find out later down the line.
Maybe.
If we find a way where there shouldn't be one.
To be clear, I mean, this was all I was intending to present, at least in terms of Connect 4. Like, we've accomplished what we wanted to accomplish. Oh, no, that's actually not entirely true. There's a way you can accelerate this. We can cut out probably a third of the bitwise operators here. Any ideas? Maybe not a third, probably not a third, but we can cut out a bit of them. No pun intended. Specifically in the is one I'm talking about.
Oh, you can compose them? So you just have the 7 and the unshifted and or shifted by 1, right? And then you
for the
duplicate
left
that.
runs?
Yeah. And then you duplicate that and shift that by...
Yeah.
So you're reusing your previously shifted...
What do I shift it by? Tell me. I think you have it, but I don't want to write it until no spoiling.
I think 2 as well.
Yeah, okay,
So,
yeah, exactly.
Yeah, yeah.
So the idea here is we're going to say uint64... well, actually, I'm just gonna overwrite what I've got here. So, no, I can't overwrite what I've got here. We have to say uint64 t left runs half is bitboard and bitboard right shift 1. Now, left runs is going to be left runs half. Hold on. Yeah, we're gonna do left runs half and left runs half right shift by 2. Does that make sense? Why this is the same thing as we were saying before, but doing less work?
The compiler won't figure that out for us.
I don't think so. That's a great question. I can't tell you what the compiler knows and doesn't know.
I don't think it would do that, because this is not like a thing that you would expect out of code normally.
Okay.
I don't know. I
don't think a case like this is accounted for.
I won't make any guesses one way or the other.
Unless it's a common thing to try and find long strings of ones in int. I don't think the compiler would optimize for it.
Yeah, so the idea would then just be duplicate that idea for all these other checks, and then you return true if it's 1, false if it's not. Cool. I think that's a good Connect 4 example. Any questions? Any lingering comments? Want to try a different board game or a different something else?
I just had one sort of. So I don't do, coding with bits very often.
Mm-hmm.
And I had a question about. So we have this. We're passing in this bool for is red.
Yeah.
But like in a real game, you know whose turn it is by the number of pieces on the board.
That's true.
And so can we call? I tried looking up like pop count or something.
Yes. Yeah, I'm glad you brought it up. Yes, pop count is used enormously in things like this. So pop count is a specific instruction that exists on. I think it's fast. I don't know. I don't know
if you have x86 and maybe not if you don't or something.
I think on a lot of old CPU
has like it probably has a dedicated bit counter circuit inside it.
I think that's what's going on.
Pop count in like Diamond Later,
which is why it would be fast.
Yeah.
In the CPU that I've made, I don't have that. So to count the number of bits, you'd have to do a loop manually shifting by 1 and counting it up.
There's actually there's a really good log time method for bit counting.
Ooh,
what is it?
Oh, here, hold on. I'll send some code over.
Yeah, it is the case that Jakob said Othello as the next thing that we could try. The interesting thing is, if you actually if you download Othello, like the all of the leading Othello solvers, like for example, N-Test is one of them, EDAX is another one. You'll see advertised on the readmes on the GitHub of all of them, both of them. Most of them, I don't know. All of the ones that I've ever seen have explicitly said your CPU has to be newer than like 2003 because if it doesn't, it probably doesn't support pop count like natively.
I found I'll put it in the chat here. I found an implementation I have of this, with of course some terrible naming conventions, but don't worry about it. And I forgot to annotate that as C, the syntax editor.
I'm gonna copy it into the, just for the sake of recording. I'm gonna copy pop count into here. Okay, so we're trying to count the amount of ones in something. Okay, so this is saying if we have pop count on the CPU, we do this thing, but I'm going to delete that because we don't care about that. That's boring.
So it's literally just adding the two side-by-side bits into a 2-bit number, and then each of those 2-bit numbers into 4-bit numbers, and then each 4-bit number into 8, and so on.
Wait, hold on. 2 side-by-side. X minus equals X.
Yeah, the initial one is kind of fucking crazy, like because it winds up just being easier to. For some reason, the resource I got this from was like Bitwise Hacking Tricks was the name of the webpage. I might be able to archive it for you eventually.
I think I've seen that before, actually.
Yeah.
So this is like for a CPU that doesn't have that kind of circuit.
Yeah.
Yeah, you could do it relatively.
That was what they were doing here with the. That's what they were doing with the.
Useful for me as well, considering mine doesn't.
Yeah, on the right. So,
you cut out there. I got robot noises.
most significant bit. Yeah.
Say that again.
Oh, shit. Excuse me. Oh crap.
Oh, good. No worries.
I was saying.
Is it a me problem?
Not again.
Or can you? Oh no. Okay. It's not a me problem.
No, it's not you. I also can't hear what's being said.
Yeah. Yeah, you cut out.
Okay, we're gonna figure this out though. This is my pop quiz for me because I've asked you guys enough questions already. So x minus equals.
We're back.
Welcome back.
Okay.
Nice. Okay, what was that you were trying to say the past 2 times?
Oh god. If you have fast pop count, you can do relatively fast count tailing and leading zero.
count tailing end of you cut out once more. Count tailing end of
Count
the amount
tailing
of
and
ones at
leading
the end.
zeros. And leading
What is
zeros.
that? What is that? Oh, count.
So like you can
count the
and
tailing
leading.
and the
I see. In log time, by fast. I
Yeah.
assume you mean. Huh. Okay. How does this work? So we're shifting 1, we're shifting 2, we're shifting 4, we're shifting 8, we're shifting 16. What's the logic
we're treating the register as basically we're just pretending we have vector math more or less. So we're doing a sum of 2-bit, we're doing a sum of 1-bit to 2-bit registers. Then we're doing a sum of 2-bit to 4-bit registers, or actually 2 to, and then we just keep going.
You're saying the sum of 1-bit to 2-bit registers is this thing? Is that what you're saying?
Basically, yeah. So like that takes each
We're
pair
saying
of bits.
X. Okay, so we're saying X takes this, like this is going to do something to X. It's going to take each pair of 2 bits and what is 0x555? What is this in like?
That's 0101.
That's 0101.
Indefinitely like that.
Yeah.
And 333 is the same as
0011.
001.
Oh, and that's the binary pattern. That makes like for
right.
That is really clever. Wow.
So we cut out. Yeah. So we're cutting out.
Like the logic gate pattern.
Yep. Yeah.
0111. Yeah.
So like after this check, like underscore X is going to be both of the things. It's going. This is the. Wait. Hold on. Haven't you lost information here? In the first line. Like so the way that I'm. Oh, sorry. Minus equals. Why is it minus equals? I didn't notice that. So.
Because it's such a small number that the sign doesn't really. I think that you can just kind of get away with like mashing the sign completely, like for a sum of 1-bit numbers to a 2-bit sum.
So we're aligning. Okay, the way I'm thinking of this is we're aligning the second bit, like the 2's bit, with the 1's bit. Then we and it just to cut out all of the junk that was in the 1's bit position. So now we have like. A bit mask that is holding the 2's bits alone on top of the entire number. And then you subtract it. Why do you subtract it? I can't visualize that. You subtract the 1's bit.
So that's the whole number shifted to the right by 1. Then you only get every other bit after you've shifted to the right by 1.
Yeah, so you're cutting the 2's bit out of every pair, and you're subtracting that out of the whole number
from the. Which would.
There's some 2's complement stuff going on here that I'm not able to quickly imagine.
Would that?
But I get the idea. I think I get the flavor of what's going on.
The initial statement is hard to parse, but like you can unwind it kind of backwards, starting from the second one as well. Like it does work the same way if you just do like X shifted right 1 and hex 55555 plus hex or underscore X and 5555, etc. Like you can't just duplicate basically the second line to be the first, but it is like it does wind up being more instructions.
The second line to be the first. You're saying the second line can...
Rather, like you can sort of work your way backwards to like. So if you copy that second line, and then comment out the initial line, we can sort of recreate the same like logic there. Like so, like that 2 becomes a 1, and then both those masks become 55555.
Oh yeah. That makes sense. Okay, so this is the 2's bit. And we added. Oh, that makes perfect sense. So wait, the right shifted one we're ending by 555. The other one we should be ending by not 555. Yeah, no, we should be ending by 555. And now we just and like. Do you guys follow that? Here, I'll try and explain what's going on. So like, we now have imagine our number is like we're just gonna do an 8-bit number. So we'll do like 001111. Now what we're gonna have there is like X right shift 1. We're gonna be taking like these two ones and right shifting them on top of these two ones, and both of them we're gonna end by the bit mask that only selects the ones column out of every pair. So we have like 20101 pairs, and you just arithmetically add those two things together, and then that'll do the same thing as just like, you know, within each pair, counting the number of ones that was in that pair to begin with.
Oh, okay. I get it. Finally.
Yeah. And I guess the line that was there before was just some simplification.
Dividing the whole number itself into chunks and counting only within those chunks, and then building this up for larger chunks and just merging together the sums.
Yeah.
Yeah,
that's why shifting right by 1 and then by 2, then by 4, then by 8.
Yep.
Because it's merging the counted chunks together.
I do think this is actually how count leading zeros from count. I think it's all actually built on this for at least like Cortex M0 and M0 Plus like ARM processors. Like I think this is actually what's going on under the hood there.
So wait, but so the second line here. No, I get it. Yeah, that makes sense. You're just doing the same thing, but with a mask for like a mask that looks like this number that I wrote down earlier.
It's worth noting you typically have to like be more careful about doing arithmetic inside of like when you're pretending your registers are actually vector registers. You need to be more careful about like masking out overflows and stuff like that. But in this case specifically, right, like the growth of the size of our sums, like in terms of the register space we get to store them in, like grows fast enough that we don't need to worry about overflow.
Why would you need to worry about overflow? Like we're only right shifting.
Pretend you add pretend you're just like treating two 16-bit registers as like a pair of 8-bit numbers like each, and then something like that, and then you add like 127 or something in the bottom like to each of one of them, and then they magically overflow into the other vector component, and you don't want that.
Right. Yeah. I gotcha. That's very cool. I did not know this existed.
There's a bunch of other... I actually compiled a bunch of very strange, like, count tailing zeros and, like, count leading zero algorithms. Like, there's some very weird stuff you can do with, like, modular arithmetic. Get count tailing zeros.
I'm sure you can. It reminds me of, like, that Quake fast inverse square root thing.
There's also the... I call it the MSDL.
Relies on the... Go first.
It's super easy, but like it's just the same kind of thing. It's like this is about the simplest sort of like stemmed within a register kind of stuff you can do. I'll put it in the chat again. Like this literally just fills the most significant bit down to the least significant bit for a 32-bit register.
What does it mean to fill the most significant bit?
So like if there's a set bit in the 14th position of like a 32-bit integer, it'll like set all of the bits lower than it.
You mean the 15th position, the most significant bit?
Well, whichever position, yeah. So it takes the most significant bit and produces a mask with every bit set lower than that position, and including that position as well.
X or equals X right shift 1.
So it's just smearing out the highest one bit, basically.
Oh, I see.
So you don't like if it was a, if it was a 32-bit integer, you don't have to do that 32 times loop.
Yeah.
You just have to do it 5 times there.
This smears out the numbers. So the goal is to get the rightmost like big chunk to be 1, like starting from the leftmost one, and then
or if it's 0, then
what is
it
this
should all be 0
measuring?
as well.
What is the goal of this function? Yeah,
so
if it's 0,
this allows you to do things like if you add 1 to that mask, you can use that same carries trick I was talking about to like get the highest set bit, like the most significant bit alone.
But how do we like from the smear? What's going on here? Like from the smear, how do we
recover? So if you add 1 to that, if you add 1 to that, you'll get the most significant bit mask of that.
But you don't have it as a. you don't have it as a coordinate. It's not a counter. It's just
Yeah.
I guess you could run pop count then to figure out the amount.
Yeah, that can also happen.
Yeah. Cool. Yeah, that makes sense.
Yeah, I think I'm going to have to head out, but this has been great. Thank you.
Thanks for coming.
For talking through stuff.
Oh, I have a good one. I did also find that parallel like neighbor counting stuff. I did. Oh, here I can send that code in as well.
A lot of the binary stuff relies on the fact that it's all modular arithmetic. Like, even the way that, like, addition works itself, like, with the whole 2's complement, it all relies on the fact that it's modular, and you just ignore the overflow. Because, like, adding a negative number with 2's complement is just doing an overflow in modular arithmetic. It's the same thing.
Mm-hmm. Yeah.
And
so I kind of gave up in the middle of this because I was trying to figure out how to do like the entire Game of Life logic in like a parallelizable way.
Wait, so you're saying this is for Game of Life? Parallel.
Yes,
what does parallel 3 count mean?
So parallel 3 count spits out basically the neighbor count. If you pretend like so you have 3 rows basically of the grid, which are R0, R1, and R2 in parallel count, and then you have the rows to the left of those as well.
So
I can fix it up.
Can't we wait? Why can't we just do pop count and like? Oh, wait a minute. Never mind. Sorry, continue. I'm talking.
Because I want to get the neighbor counts in parallel. Yeah. Like it's kind of annoying, so I had to write this weird.
I hold on. I don't know what you mean by parallel 3 count. Like parallel 3.
Okay, so that
what is the what are the inputs and outputs here? Before you tell me what we're doing.
Yeah.
No. Sorry. Well, pretend. What's the goal? What is the intended input and output? Like, what is my doxygen string at the top here? Like,
this will count for each basically cell in a center column of like 64-bit cells, living or dead cells, right? This will count the 8 neighbors given the row above and below it, or at least the number of
row above and below it. What do you mean by the row?
So, like, if we're looking at 3 rows at a time, basically, of the game board. And
is that what R0, R1, R2? That's like the. So looking at this board, like if we're concerned with this spot right here, this 0, then you're given row 0, row 1, row 2. Is that the idea?
Yes, that is the idea.
Okay, and then
we're figuring out
this
the neighbor counts for R1 specifically.
RL0, RL1, RL2, are those columns?
No, those are the rows to the left of row 0, row 1, and row 2, respectively.
What do you mean by to the left?
So literally like on the bitboard, so that I can store like a bitboard that's wider than 64 bits, basically. Like the idea was I wanted to like be vectorizable across an arbitrarily wide like golf field, basically. Okay. So I have to be able to pass
so this is like gotcha. So RL0 is like, is that the one that's left of us right now?
Yes. So RL0 is the row is the bitboard representing the row to the left of R0. RL1 is the bitboard representing the row to the left of R1, and so on.
Okay.
And then so the reason there's 2 outputs is rather interesting, and it's because the top and bottom, right? If you add the number of neighbors in the top and bottom rows, that can be at most 6. Right, that fits in 3 bits, but 8 does not. Right, 8 will overflow. So
what is our goal? Wait, why is 3 bits are like? Hold on, let me figure out what you're doing here to begin with. Like top bottom. What is top bottom? R0. Okay, so I can see why you're doing this. I get the principle behind.
Also, that's actually a typo. Those should be 63 instead of 31.
Sure, that makes sense. But like so this is we're just treating it as a whole larger integer, like using both of them at the same time.
Yeah, we're rotating that in the left neighbor in basically.
Top bottom. What is this a like your?
That's an output variable.
Wait, why are we setting the pointer?
We're not set.
Wait.
We're
Oh,
dereferencing.
you're assigning. Oh, gotcha. Oh, sorry.
So
This
top, bottom, and
is
side are both.
this
Those
is
are output
C
variables. Yes.
as opposed to C++. So you don't have pass by reference. Is that what's going on? I rarely
No,
write
no,
in
those
C.
are those are being modified. Yeah. Well, so yes, I know.
Well, it's implicit pass by reference, but not like the C++
Yeah.
style, like with the ampersand.
Yeah. Sorry.
Gotcha. No, I follow you now. I follow you now. Okay, yeah. Sorry, I'm just not used to this like notate. Like I get the pointer arithmetic, but I'm notationally used to having an ampersand instead of pointering. But no, I got you. Okay, so the idea by this first chunk is we're
literally incrementing a 3-bit
counting
parallel register 6 times.
But the goal, what do we want stored in top bottom?
Basically a strip of 3-bit sums that represent the neighbor count excluding the side squares of each center.
A strip of 3-bit sums. Where does the strip exist?
So we're basically turning each what am I trying to say here?
R0 and every 3rd bit plus row 0. Why is it top? Like, are we not looking at top and bottom? What is side? What's the geometric meaning of top?
Bottom? Side is going to be either 0, 1, or 2, depending on whether there's 0, 1, or 2 neighbors alive on the side cells of the given cell corresponding to like where it is in that register.
We're concerned with this. Like, wait a minute. How do we even? This is like this strip of bits, but we don't know where the bit that we're concerned with is.
We're doing all of them at the same time. The idea is that we're getting 64 divided by 3 neighbor counts at the same time.
But R0. But we've lost information. If R0, R1, and R2 are just a strip of this stuff, then
here, do you want me to give you the usage code like directly? Let me check to make sure it actually.
Maybe that will help. I'm not sure. Maybe it will. Maybe it won't. I'm still lost on what the principle is here. But like, what would this look like, for example? Like, if it's something that you can say in hex easily, maybe could you say it in hex? An example of what that might be.
An example of what in particular?
R0. Like, would that be a full bitboard? Or would it just be one strip?
That would just be a single row. That would just be a single row of, like, say, a gallboard.
But if it's a single row, then how are you going to do anything other than the information in those rows, those 3 rows? Are we doing one row at a time?
You're getting the neighbor counts for one row at a time, but you're also using the rows above and you also have access to the rows above and below it.
You're getting the neighbor count. We're getting the neighbor count yeah, so we're populating this, like, this is the row that we're going to be writing to. Is that the idea?
We're not writing to any of the rows in this function yet. We're literally just getting a. Okay, hold on. I might be able to diagram this out in Notepad. Literally.
Yes, please.
We share a screen. Apologies for the 720p. So, say we
no worries. I'm gonna switch my OBS to look at you now. Hold on.
Oh boy. So maybe we have like something like this, right? Like, pretend we're doing like 8-bit instead of 64-bit, and we're just gonna completely forget that there are rows to the left and right of this thing. So this is gonna be a blinker, right, in a game of life, or something like that, right? So the idea is that what we do is, for say like we want to work out like the neighbor counts for like this cell, right? Like right here. So X, right? We're gonna mark that one. So like we can do this by basically, so this is where the top and bottom basically are going to be the population count of these 6 bits, right? And then
Uh-huh.
side is going to be the population count of these 2 bits, more or
Okay,
less.
yeah.
And then
X is the one that we're
so
concerned with, and we're aiming to have a value of 1 that we find.
right.
Okay.
So
So we have, and we're populating we're populating top, bottom, and side. Why do we want to populate those separately? Like, what's the constraint? Because we can still fit
because
a 0 to
well,
8 in. Oh, because
the
8
idea
itself is.
that would
You would need a
overflow,
4th bit. Yeah. Yeah. Okay. Yeah. I follow.
So the idea is that we can keep everything kind of simmed within a register nice if we do
Yep.
like
A top bottom
basically
split and
mask
then
all
and then
these
a
and
left
then,
right split. Okay.
so
Yeah. I
we
follow.
can use I had somewhere to go with this. Somewhere else. I can't remember exactly where. I was going to try to actually do like an evolution step, I think, but that would be really, really hard. I still haven't quite figured out how to do like the Gauss logic in parallel. Like on even given like the top, bottom, and side neighbor counts, like all the cells. But the code that actually like basically there is also a there's another caveat, which is that you have to do it 3 times, basically, because you only get the counts for every 3rd cell.
You only get the counts for every 3rd cell.
At least if you do it the way I did.
Why do you say that? Oh, right. Yeah. Yeah. Okay. Yeah. Because you're just tossing out all of the data for everything else. Yeah.
Right. So there's some
Okay. Yeah. I'm gonna have to.
This shit just it got kind of nuts. I couldn't. I don't even think I could explain to you like how I derived like these at this point.
Yeah, mine got nuts too when I started doing this. I ended up losing the plot. I had like, I did everything all at once, but I think I had a lot more like intermediate variables and stuff. I think what I was trying to do was like, I would take. I think I had instead of populating the counts, like in the rows and columns of the board itself, I had them populated across like different bit boards. So like I would have a bit board of 1s, like 1s places, and then a bit board of 2s places and a bit board of 4s places, or something like that. Although this was months ago, so I've forgotten exactly how I did it, but I think that was the principle.
I'm trying to remember exactly now what this code does. So like I have these parallel 3 counts, and then I try to subtract like the total like population count from 3. And then like if the difference if that difference, which I can fit in 3 bits even signed, is less than 0 or greater than 1, and the cell's overpopulated or underpopulated. What do I mean by this?
Well, that's like those are the rules of the game of life.
I'm trying to figure out like I don't know what the hell I was doing here.
If the difference is 0, the difference between what and what? I'm not sure.
If the difference between the number of cells, the neighbor counts, and 3 is 0. So if the number of cells is exactly 3, right, the cell will be 1. Like, of course, and then.
I think you may have given me a great idea on how to do this. I think now that I know that all these tricks for pop count, that might be the key to like being able to populate in the way that I mentioned, where you have like different bit boards for different place, like different digits in binary.
The smearing bits around and like bit group moving stuff is like very helpful, actually, especially for like
that seems helpful.
Like format conversions and all that stuff.
Right. I'll have to try that.
Let's be manual. So like yeah, I had some example bitboard. I think this is actually broken. It's like I'm doing a couple generations here. And of course like it literally takes no time to run the global evolution steps.
Yeah, 0 seconds.
Like literally I don't even think clock is picking it up. That's not funny. like printing it out is probably taking a lot more time.
Probably. Anyway, Jacob asked for Othello, but honestly I'm kind of tired. Maybe.
Oh, I stopped
I
streaming.
thought it was. Yeah. Yeah, that's okay. I thought it was kind of hard
You can always figure
to.
it out on your own time.
I'm trying to think of off the top of my head. Maybe I'll end like this. Just to. Maybe we could do some design questions. I'll say this: when I implemented my Klotsky solution for my last video, I did not use Bitboards, and I totally regretted it afterwards.
Oof.
Can you think of a good way to use Bitboards there? I don't know why. I think I just started writing it and I wasn't in the mindset. No, I know why. It's because I copied code that I had from years ago, and when I didn't know how Bitboards actually worked, and I think I just never bothered updating it.
I can find you some references I used to come up with a lot of the, like, just my whatever stuff in my pocket, I guess. Let me find actually some.
Yeah. But like, so what do you guys have a good idea on how you would use that for such a purpose? How you could use Bitboards for that? I think this is a good mental exercise if you can describe an implementation of Klotsky using Bitboards. For quick movement, for quick collision checking, for quick
I got it.
move
Would
legality
probably
checking.
Be flipping off the bits it moved from and flipping on the bits it moved to.
Yeah. In the case of Connect 4, we had to have 2 Bitboards. How many would you need for a Klotsky board?
I assume you would need one for each piece.
Yeah, and I think Jakob probably knows more about this than me, but I think that's what you do in chess as well. Each chess piece or each like type of chess piece has its own like
I would assume
field.
per type.
Magic Bitboards are a thing too, and I don't know about them. I've read about them, but I've forgotten how they actually work. You use clever multiplication tricks. I wish you could join and explain over voice. Magic Bitboards. Mask the relevant occupancy bits. I'm reading that page. I just realized I'm probably not sharing the right screen anymore, if I'm even sharing any screen.
Nope. Can't see anything.
Shoot. Okay, this will be homework reading. I've vaguely heard about these in the past, but I've never gotten around to learning about them. Is it specifically a chess thing? Is this like...
They're very common in like chess programming, yeah.
But outside, I mean,
like,
outside of chess, are they useful outside of chess?
Yeah, I guess we use
it
graphics
translate over to
programming a little
Klotsky.
bit for like masking operations.
Oh yeah, huh?
Yeah, moving a piece in Klotsky would be easy, I would think, right?
Yeah, just a bit shift.
Yeah, you bit shift by the row or by the column, and you can just use an XOR.
How would you How would you efficiently do collision checking?
You can just do an OR with, an AND with all the other bit boards and check if there's a 1 in any of them.
Each of the other bit boards?
No, you just AND all the bit boards together.
That's a lot of ANDs. You can do better.
It is, but you can do a binary tree type AND.
No.
You can like smear a block along its trajectory using that like fast set bit.
No, but the problem is that if the problem that I'm trying to highlight is if you have one board for each piece, then you're checking collision by iterating over either implicitly or explicitly, like inline. You're ANDing with every other board. So how can you avoid the need to AND with every other bit board for all of the other pieces one by one? Because like now the amount of ORs that you do is a function of the amount of bit boards that you have. And also, in addition to that, implicitly you now have to somehow use a loop to like iterate over that set of boards, because you would presumably have them in an array because you want your thing to be agnostic to the amount of pieces that your puzzle has. Keep a redundant mask bitboard is what Jakob says, and I think that's the right idea, but could you explain a little bit more as to what you mean by a redundant mask bitboard?
Like ORing all the pieces together first, because you're going to have to do that anyways. You're always going to have to do that. So you have all the general board that's ORed together. You XOR with the single piece that you have to remove it from the general board.
Yes.
And then you move it, and then you AND it with the general board and check if it's a 1. If there's a 1, then it collided with something. But if there's no 1s and it didn't collide,
yep,
then you can OR it back in, and that's your move.
Yeah, that's it. Beautiful.
Because
which is also making me realize that what you just said made me realize that there was a faster way that we could have done this. I did this weird not thing where I said and not full board, but this could have just been an XOR. We just saved one clock cycle.
XOR is cool.
XOR is cool.
I'm suddenly remembering a little a little programming challenge. There is an array of characters.
Hold on,
right?
sorry. I was pointing at something. Let me share my screen one more time.
There's probably a quote-unquote bitboard algorithm for comparing double precision floating point numbers.
I bet you there is. You probably could.
Yeah, I'm suddenly reminded of a little programming challenge.
Wait, I think I might actually have
I did not figure out the easy way for.
You could like snip out the mantissa, snip out the...
It doesn't matter what the characters are.
Oh yeah, hold on. I have the here's the I think this is actually IEEE 754 soft float compatible. Here, one sec.
I don't know what soft
within this
floats
array
are.
of characters.
I think this is like IEEE 754 accurate.
I don't know. I don't know what you're talking about. What's that?
Like,
oh, IEEE 754 is the floating point standard.
Why would we care about it if it wasn't compatible with that? Isn't that a given?
I mean, there's more than one floating. There's more than one way to do floating.
Yeah, like Google has a bfloat16, which is a different form of 16-bit floating point numbers that has an 8-bit exponent instead of a 5-bit exponent, and they use it for AI models. The standard uses a 5-bit exponent.
Huh. Why do they use it?
This
why
one's
is
more
there
of a
more precision.
Second
range.
8
8-bit exponent means more range, but less precision.
All right, are you ready? This is the bitboard algorithm for comparing two double precision floating point numbers for equality, including sine 0.
Holy crap! Wait, I want to read this.
So I actually have a better for single precision. I documented it better, but basically the gist is let me actually for real comment this.
Okay, double sine bit. Okay, so we cut out the sine, we cut out the mantissa, we cut out the exponent. Oh, so float and double have different bits. Okay, sure.
Here's let me replace it with the I'm gonna update it actually so it's a little more readable.
Yeah, a float has an 8-bit exponent. I think a double has I forgot.
I'll just
that
throw
looks
all
right.
of
This
them
is
in there.
this is 8. This is 15. No, not 15.
15-bit exponent.
This is sorry, 11.
I updated it.
11-bit exponent. Yeah.
What are these?
It has one.
What are these comments?
1.7.
Comments are for the weak of spirit. Sorry.
Floating point infinity.
What'd you say? I missed you.
I have the number 1.79E308 memorized because it's 64-bit floating point infinity. Because I played this game called Antimatter Dimensions.
179. Huh?
1.79 E308.
What is that?
Floating point infinity.
Oh, you haven't memorized why?
I played this little game called Antimatter Dimensions.
And they have and that's what comes. Shoot, why can't
And
I'm having
the first goal you reach is hitting infinity. Because it gets numbers that big.
Nice.
They messed with
Burned
the
into
code
your
so
brain.
much that you can't hit floating point infinity anymore. They managed to get above it.
Okay, what are we doing here? Comparing equal. Wait, this is comparing equality? Oh,
Yep.
but it's returning. Yes, it's returning. Like, we're not just doing equality. We're checking equality and greater than and less than, right?
Well, it's weird because their signed zeros are both equal to like -0 equals +0, but they both have different representations.
Wait, was that the goal to begin with? I thought the goal was to check like greater than and less than.
Well, I have those too. One second.
Oh my god. Wait, hold on. I want to read this. That's okay. I'm already tired, so I don't know if I want to go through all like that sounds harder. If this one's this long,
It's actually
then, like,
it's
I don't
kind of
know.
fun. So it works because you can if you treat floating point like the binary representation of a floating point number as a sign magnitude integer instead of a 2's complement. Like if you just have the sign is like an actual sign flag, like times -1 or +1, and then the rest of it's just like a magnitude, then you can actually compare the integers lexicographically.
What?
Or you can literally compare floating point numbers like because of the exponent, at least if they're normalized.
Oh my god, you're right,
and they
aren't
always
you?
should be. They always should be normalized. If they're not normalized,
No, they
then
have.
because of
No, they have to be normalized. They can't not be normalized because there's an implicit 1 to start, isn't there?
Yeah.
So like, non-normalized floats are unrepresentable,
Yeah.
if I'm not wrong.
And then you can literally get the lexicographically next, like, single precision or double precision floating point number by incrementing it. It's kind of crazy.
Holy crap! I never realized that. That is cool as hell. That was probably in some comp org class that I wasn't paying attention
Dude, there's so much shit packed in the standard that's like
great.
really hard. Yeah. Yeah, it's literally the only reason you can like do floating point comparisons like with
Except
any speed whatsoever on
subnormals.
like microcontrollers.
Yes, probably except subnormals. I don't know, but I can't imagine this actually extends entirely because there's just so many weird
Subnormals are
edge
just
cases.
linearly spaced, so it might work. I think you can. Yeah, it should be fine. Actually,
is it? I don't know how they get represented.
yeah, because
like,
so the subnormals
what's the representation for them?
Yeah, I gotta make a talk for it. Fuck, I actually probably could.
You should. Actually, you know, one talk that I saw. I'll pose this as a puzzle or a little question. How many, like, if I were to write some code that generates a random floating point number, we'll say a 32-bit float, and takes the sign of it according to like the standard C sign function, although it turns out the implementation doesn't really matter that much. I'll
bet it's probably. Sorry, continue.
What is the probability that randomly chosen float is its own sign?
I remember there being some estimates in the comp sci chat, maybe.
Did we talk about that there?
I think we might have, yeah. But I'll bet it's a pretty similar ratio to the fraction of floating point numbers for which e to the x minus 1 equals x, like close enough.
E to the x minus 1. Is that x minus 1?
Sorry, e to the x parentheses altogether minus 1.
Gotcha. Yeah, it's probably similar. I mean, you also have a slope of 1 there, and like there's the small x approximation is still like it still works. You still have x
also tan h of x and so on.
Right. Yeah, you can. I mean, you can come up with a very simple first guess, like a very naive first guess, without much knowledge of anything. If you want to take a stab, like.
Probably at least half of them.
I sent the puzzle that I remembered in the show and tell chat.
At least is not correct.
At most half of them? Wait,
at most half of them. Half of them bounds it by above. But, although it's a somewhat tight bound.
Okay.
I mean, the reason is
I would say it's got to be a lot of them because like
it's a lot of them.
There's just so many. I mean, there's not as many around 1 as there are 0, but they're still like really clustered around 1.
Clustered around 1.
Or
Sorry,
not clustered around, but they're really
clustered around 0, right? We're concerned with clustered
they're
around
clustered
0.
around 0, but they're still really dense around 1.
Yeah, they're still really dense around 1. But
why do I care about the density around 1? These are small angle.
Yeah, I don't know why you care about that. Right.
Oops.
But yeah, like I mean, just think of it like, the mantissa is the exponent is either positive or negative, and like roughly half of them are positive, half of them are negative. So like all you need to be able to achieve a very a very small number is for that exponent to be like sufficiently small, as in like less than -6 or something like that. So that just serves like, what's the set that have an exponent that's less than -6, and you can work out all the math, and you can actually like rather close, like you can approximate very well by
I would look at like what does the Taylor approximation around 0, like basically how small am I allowed to make that error before it just doesn't do anything.
You can do that, and it pretty much gives you the exact right answer. And I'll spoil it. That turns out to be like 45%. 45% of them are their own signs.
Yeah, that feels right.
Yep.
I wonder.
I lost you again. Audio wise, you cut out.
Probably.
You cut out. You cut out. I couldn't hear you.
Oh, I said I wonder how that trends if you go to double precision.
I'm imagining it just halves, like naively, because we increased the exponent by.
Because now you have 20, or no, you have I forget the breakdown.
Yeah, no, wait, it's not naive having. So, well, just from the code that you wrote here, it says 7f8 for the float exponent bits and 7ff for the double exponent bits. So we've increased by 3 from 8 bits to 11 bits. So the amount of the amount of representable exponents has gone up by a factor of 8. So I'm imagining that the percentage, like the deviation from 50%, will shrink by a factor of 8. So does that vibe?
Yeah,
with you?
I guess so. So it should get closer to half.
It should get closer to half by a factor of 8, I think.
Forget exactly how to do the. Well, I guess I'll just drop the. There's also like funky like optimized.
I lost you again. You cut out again.
Damn it! I said there are like also optimized like comparisons to 0 specifically, which are great for floating point representations.
Wait, what? Optimized comparisons to 0. What does that mean?
So
comparisons to
x equals 0, x not equal to 0, x less than 0, less than or equal, etc.
Including. I thought you meant equality specifically. I was like, so just check if it's 0. But no, I see what you mean. But wait, can't you just check the sign bit?
For most intents and purposes, it gets weird because -0 is equal to +0.
Sure. Okay. Yeah. When you say there's optimized, are you saying there's optimized implementations in hardware, or are you saying that there's?
Well, I mean, you could implement it in hardware. There's kind of not really any need to, because the comparisons aren't really the annoying thing to do on the ALU. Like it's really is just like accelerating things like count leading zeros and like shuffling the bits around so you're adding to the right power. But like here's in software. I'm dropping more code in chat. Like these are all so if you have like double precision subtraction, if you have floating point subtraction just like given to you, right, or something like that, then you can just use these.
I don't even know how to read these. What is this? CMP? What is CMPL? CMPEQ? Compare equal.
equals 0. Yeah,
Zermelo-Frankel
this,
set
like, sort of
theory. No.
these are like Intel semantics. These are like assembly
Gotcha.
semantics that I'm sort of duplicating.
What is ZF?
Float versus double is what the
What
D
is
versus
Z?
F. 0.
Okay, gotcha.
So yeah, all of these are specifically for 0.
Yeah, that makes sense. What is interrep F? Is that like casting it as an integer or something?
That's the integer representation
Gotcha.
of it. So and then that actually there is a completely defined behavior way to do that. Actually, the government doesn't want you to know, but you actually can type on floats as integers, and it's like, okay, here, this is I'm gonna give you the good stuff.
Give me the good stuff. I think that would be a perfect way to end the interrupt D. This thing here, interrupt D in this one.
Intrap app is the most explanatory one.
Floats are magic.
Interrupt F. Where's interrupt F? Oh, I see. Top. Lots of.
I remember there being another kind of float that has 2 sets of exponent bits, like an exponent for the exponent.
Hold on, I'm trying to read this implementation. Requires type pun. In 32. You're just mem copying. No, sorry. This is the bad solution. Is that what's going on here?
Yeah, there's pointer mashing at the top. Then you have mem copy.
Right. Okay. Yeah. This is these are two different implementations that suck. Oh. How do unions work?
So it's like a struct, except one member is only allowed to use the data at a time, basically.
Oh, like a what are they called? Like arithmetic type. What's the word for it? Like in Haskell, where they have you have type that is, it's either like an additive types or multiplicative types. I forget the fancy term.
The point is that like the size of a union in bytes is bounded by its largest member.
Yeah, so it's like an either or type of data type.
Yeah.
T equals dot F.
Yeah, member assignment and C is
dot F equals underscore X.
You assign the floating point member and then you read the integer member.
Wait, so we're defining a T. We're defining this T of the type of this union that we've just created, and we're saying that T is equal to what's dot F? Oh, T's being constructed such that
its
F
floating point member
equals underscore X. I see. Huh.
And then the same thing works going backwards.
That's insane.
Yeah, it is. It is pretty insane. It is entirely well-defined behavior up to how floating point is defined. So you're going to get some interesting results if you execute this on alien computers with alien FPUs. That I don't know. Throw the sign in the middle of the representation or something like that.
Yeah. Oh, you mean yeah, interrupt would still work, just all the comparisons would stop working because you're assuming sign bit does some things.
You know.
Yeah.
They don't compare lexicographically, they compare by something else.
Right. Okay, thank you for showing me the government secrets.
You're welcome. Anytime.
I'm gonna stop recording.
Let me know if you ever need help on a Bitboards video. I'd be happy to work on that.
I don't know how I would make that pretty.
That's maybe like it would have to be
black
like
and white tiles,
lots and lots of like matrix. I would honestly do like the Manum style like matrix drawings and stuff like that.
I'm not gonna do that
any
though.
Better way to do it.
That's not my character.
I get it.
I also don't like Python. What's that? What about tiles?
Black and white tiles.
Yeah, but that's not like in your face crazy visuals.
It would have to be
Yeah,
like
true.
some side by side visualization of like what's going on in like a bunch of registers and then what's also going on like in our
Yeah.
2D representation, which would be kind of weird.
Yeah.
Like, but
Maybe
I mean,
someday.
actually, that would be that's not
You should do it.
too
Sounds like
broad.
you're
I guess.
sounds like you're into it. I think you should make one.
I will
Yeah.
see what I can. I'm not very good at like the animation. I might go for your whole swap tube.
Do it, do it,
Roll.
do
We'll
it.
see.
Sweet. Okay, I'm gonna drop. I'm tired. It's 11.
Have a good one.
Bye bye.
Good talk. Good night.